Let's have new antibiotics such as our glycylcycline. So these are under tetracycline pa rin. So they have broad spectrum of activity. It has more, it is more active comparing the old tetracycline. So under our glycylcyclines, we have tetracyclines. They have a half-life of 55.4 hours, highly bound to plasma protein, mainly used as IV for skin infections and intra-abdominal infections. So these type of infections are not really life-threatening at all. Active also against MRSA and strep pneumoniae, and that is resistant to penicillin. So we have here the comparison of our drugs here. And then we have here Rolly tetracycline. So it's a semi-synthetic tetracycline, has a broad spectrum activity used especially for parenteral administration, mainly used in rickettsia and brucellosis, and recent studies trying to investigate the effect of its combination with beta-lactam, such as cefotaxime, for treating MRSA infections. So it has a new addition and this part here. Furthermore, let's understand the metabolic transformation of tetracycline. So most of them, they are excreted unchanged in urine. That is why it is toxic, because it is excreted unchanged via urine. So sulfate and glucuronide conjugates were detected in urine, especially for our doxycycline and minocycline. And the major metabolite found to be N-dealkylated at C4. So when you say N-dealkylated, you have removed the alkyls or the methyls there. And to a little extent at C7 for minocycline. Okay, so that's for our tetracyclines structure activity relationship. So let's move forward to macrolide. So macrolides, they are also antibacterials that are derived from actinomycetes. That's why they are also called as antibacterial antibiotics. So in 1950, picromycin is the first to be identified as a macrolide, followed by our famous, until right now, erythromycin. And we have carbomycin. So currently, we have more than 40 compounds that are known. So the macrolides, they have three common chemical characteristics. First, a large lactone ring, which prompted the name macrolide, and a ketone group, and also a glycosidically linked amino sugar. So usually, the lactone ring that make it a macrolide contains 12, 14, or 16 atoms. That is why it's macro. They are unsaturated, that is very lipid-loving, with an olefinic group. So it contains a lot of double bonds conjugated with ketone function. This is how the macrolide looks like. And double bonds are present. And then we have here the ketones linked. Ketones natin, yan. And then we have amino sugars that are linked glycosidically. So the macrolide, the ketones here, ketones in C1 and C9, and then we have our amino sugar linked glycosidically. So that is how a macrolide looks like. Mechanism of action and resistance. So first, in the action of our drug, it binds selectively to a specific site on the 50S ribosomal subunit to prevent the translocation step of bacterial protein synthesis. So they have the same proper mechanism of action of our tetracycline, but in the specifics, it acts on 50S ribosomes, while tetracycline acts on 30S. Bacteria produce an enzyme that methylates a specific adenine residue at the erythromycin binding site of the bacterial 50S ribosomal unit to overcome our erythromycin. So enzyme pa rin yung ginawang resistant factor ng ating bacteria to counteract the drug. So, methylated ribosomal RNA remains active in protein synthesis, but they will no longer bind erythromycin. So that leads to resistance against erythromycin. So in terms of modification of the structure, this is the places where we can add or we can modify. So here, in this part here, we can convert this to amine, or we can convert this also to oxime. And we can have another ring, or we can do ring expansion here, or we can add cycloalkanes. This part here, conversion to 11-12 cyclic derivatives that will help improve the action. And then this, in hydrogen, we can replace hydrogen with alkyls. And then this alkylation here also of hydroxyl group, this hydroxyl can be replaced with an alkyl. It is still possible. And then this one, we can cut this glutinose, this sugar here, into ketolides. So you can also modify the amino sugars for our macrolide. This is the comparison of our macrolide structures. So we have erythromycin, and then we have azithromycin and telithromycin. So I will just show it just for a glance because an activity of this is waiting for the class. Try to identify which part is unique for erythro, clarithro, azithro, and telethro. The same thing, the same way I have identified it, I have presented it to you in the tetracycline part. Okay? Erythromycin class, it can be formed as an ester. So you can, or it can be in ester formation to create prodrug, or to coat it and to allow absorption in the intestine and not be degraded in the stomach. So that is possible. So we have here erythromycin, ethyl carbonate, erythromycin stearate, erythromycin ethyl succinate, and erythromycin estolate. So these salts here, yan, they will help coat our erythromycin. So the stearate, it is a salt that is acid labile, so it can withstand our gastric juices. Ethyl succinate, it will also enhance absorption with food, so that we will not be consider dosing or right before eating or after eating. Estolate, the most acid stable, and we have the new one, glucipate. This is an IV form for Legionnaire's disease.